I introduce briefly the next speaker, the last speaker of the session, with John Canny.
Okay, I need that.
Yes, professor in computer science at UC Berkeley. John also earned a PhD in computer science from MIT, and also supervised by Thomas Lozano Perez, and for which he earned the ACM Dissertation Award for his groundbreaking contribution showing complexity of robot motion planning with algebraic worldwide methods. John is Packard and ACM Fellow and made important contribution to different research domains, ranging from computer vision, robotics, of course, AI, machine learning, and more recently, human-computer interaction. So, the talk will concern recent work he's doing on explainable and advisable self-driving vehicle control in order to improve the acceptance of trust in this system. So the floor is to you.
Thank you. It's a pleasure to be here and reflecting on Jean-Paul's work. So I've had a long trajectory in computer science and in and out of robotics, but in the early 90s, I was doing non-holonomic motion planning and interacting a lot with Jean-Paul. So I have a brief story from that period when I visited Toulouse and had a very nice dinner with Jean-Paul at a restaurant that he liked very much, which on the menu had carpaccio de boeuf à volonté, which is all-you-can-eat beef carpaccio. And I thought that was, maybe a little bit risky since it's in Toulouse, which doesn't have exactly cool weather. But I thought 1 or 2 plates, risk is probably pretty low. But we went to the restaurant, and then I realized that he's an optimum control guy. And the minimum cost solution for all-you-can-eat beef carpaccio is order all-you-can-eat beef carpaccio all evening. So we immersed ourselves in a very nice conversation about robotics and sort of lost track of time and how many plates of beef carpaccio we'd ordered. I'm pretty sure I got to about 8. And at that point, the very thin beef was starting to look really thick. And so I had to stop. But Jean-Paul did another 2 plates and kept smiling the whole time and seemed really happy. And I guess, the story has the expected end. So the next day I did suffer from some problems. I think of it as BGV, which is bathroom at grande vitesse. And so I recovered after a while and saw Jean-Paul, and he was still smiling, which shows he's a better control person than I am. Anyway, so I'm going to talk about 3 different projects that are contemporary work. So this is in the area of human-robot interaction, which is close to Jean-Paul's interests later in his career. And so what we're trying to do with this work is develop models that sit on top of self-driving vehicle controllers that provide some understanding and explanation of what they're doing, hopefully to improve acceptance of those models by human passengers. So in this work, we're not doing optimum control. We're relying on deep neural networks because they have a lot of flexibility and they can deal with a lot of real-world situations that are very difficult to formalize and plan for. But by making that trade-off, by relying on, instead of lots of data and scenarios that are real-world scenarios, you lose the understanding that you have from formal models and control techniques. So the idea of the explanations is to put some of that back, give the user some understanding of how and why the vehicle is behaving the way that it is. All right, so we'd like to enhance trust. We'd like the user also typically to have understanding in the sense of being able to expect or predict what the vehicle might do in different situations, and also to facilitate the user being able to express to the vehicle how they would like it to behave, perhaps, driving more carefully or driving more aggressively. And the explanations ideally because the user is probably doing something else in the vehicle if it has an automatic driver. They should be ideally not using the user's hands or eyes. So ideally, speech is an appropriate medium for explanations. All right, so an interesting challenge, though, with explanations in the context of self-driving vehicles is that perhaps the easiest first way you might attempt to solve the problem is by using human explanations as a training data set. One challenge, though, is that people, when they're explaining their own actions, have a strong bias to represent themselves as idealized drivers and not admit to mistakes or faults. So this list is a list of actually reported explanations of accidents. These are all English drivers, by the way. French drivers, I think, are safer, but and American drivers. But these are examples of things that people actually have said. So I'll just pick out one here. I bumped into a lamppost, which was obscured by human beings. So it's funny, but it's also, it's actually encoding a real bias which people have, which is sometimes called the fundamental attribution error, which means that if you did something bad, you tend to blame something else, the environment or other people. Whereas if somebody else does something, then they directly get the blame. So a challenge with using this kind of data is that you don't really have ground truth because people are actually more than explaining what they actually did, giving an explanation in terms of what they should have done. So a priori that seems like a negative bias, but we'll see right towards the end of the talk that it's actually a useful kind of bias that we can exploit in a different way. Okay, so also when people give explanations, at least in this kind of context, they're trying to give a causal explanation, which means they're explaining some phenomena or observation in the environment as a cause of the behavior that they made. So simplest case is if the vehicle slowed down approaching a stop sign, the explanation would be that the vehicle slowed down because of the stop sign. And what that actually means, if you sort of extrapolate in a logical sense what the meaning is, that it did slow down because of the stop sign. It did slow down. If there was no stop sign there, it should have done something different. All right, so the stop sign had some kind of direct and causal influence on the behavior of the vehicle. All right. And these explanations are actually coming from a literature in psychology on explanations which gives principles and best practices for human explanations that we were able to draw from. And at the time, Tonya Lombroso was actually at Berkeley. So a first attempt at explanations of how and why the vehicle behaves the way it does is to use visual attention. So this is inline visual attention, meaning that there's some kind of multiplying element. We can just maybe focus on one part of this big picture, because I'm not putting the right. Is it the button or something else? Ah, okay. Thanks. Yeah, so there's one, I'm still not getting it, huh? Oh well. There's one multiplicative element which has the pi in it. You can see over towards the right there. It's an inline multiplying element. Okay. Cheers. Okay. Yeah, it's an inline multiplicative element, which means that the vehicle controller, which is over here, along with figuring out how to control the vehicle, it's also computing an attention mask over the input. So in other words, it's focusing on certain parts of the image in a multiplicative way, which means effectively it's not looking at certain areas of the image, it's zeroing them out through the process of the pipeline through to the controller. So this kind of attention is very useful because it gives us ground truth for things that are not relevant to the vehicle's behavior. So it's similar to visual saliency, but it's a slightly stronger notion because it formally removes stimuli that are not relevant. Okay. So in other words, it defines true negatives. Areas of the image that don't receive any attention weight can't have an impact on the output. However, you have a problem that generally the attention is a bit too diffuse. It attends to lots of areas of the image that may have an influence, but in practice don't have any influence. So in other words, it has a fairly high false positive rate. So since we have a notion that we want important areas of the image to have a causal effect on the behavior of the vehicle, we can actually do that with a direct measurement. If we first cluster the attention into blobs like this, we don't have objects yet, they'll come later on in the work, but hopefully those blobs are aligned with objects that are part of the image. So the simplest way, if you like, of segmenting the image at this level, very elementary level, is just to cluster the blobs, which produces some discrete elements that you can then mask selectively, feed through the controller to see if it changes its output in a significant way. So it's a calculation you can actually do if the number of blobs is not too large. All right, so yeah, so in this plot you can see some attention maps for different frames of video from a sequence from actual scene. There's something else going along on this vertical axis that's not super important, but there's a formula that regularizes the amount of area of the image that's attended to, which is this lambda parameter. And you can force the attention before this causal filtering to be more sparse by making that attention weight a little bit higher. So, okay. Here's the effect of different attention weights. It makes the image generally a little bit more sparse as you increase it. But there's a trade-off. As you make the attention more sparse, attend to less of the image, you also tend to reduce control accuracy a lot. Like with this very large value of attention weight, image is very sparse, but you also have very poor control because it's evidently missing some actually important areas of the image. So these, just to clarify, I didn't fill everything in, did I? So these are errors in the controller's direction or acceleration relative to a human training trajectory. And the model becomes more accurate generally with lower attention weights, but on the other hand, there's a small range of difference. So it doesn't hurt you too much to use this kind of attention, and we can achieve a little bit more sparsification using the causal filtering that I described. So what we're aiming at here is generating a fairly simple and fairly sparse heat map across the image that gives a user that's interested enough to look at those images some idea of what the vehicle's attending to when it's making control decisions. All right. And very quickly, we don't quite see an improvement from adding this attention layer on top of the vehicle, but it doesn't hurt performance very much. I'll just summarize those results. It's not super important to look at all of them. So where we are now is that we've been able to do some sort of annotation of the scenes, individual frames of video that help us understand which parts of those images are important for the controller. But as we said earlier, we'd really like to get textual explanations of what's going on that could be fed to the driver with speech. So yes, and the secondary advantage of having a textual explanation is that you can say what kind of effect the stimulus has, as well as what the stimulus is. Whereas with the heat maps, we only get to see which area of the image is causing some effect. We don't know what the effect is necessarily. So when human beings make text descriptions, when human beings make text explanations, there's also a description of the thing being explained. That's actually quite important to resolve ambiguity. I'll show you some examples in a moment. Actually, there's some here. So a human being explaining the scene up here would say the car is heading down the street, so that's just a description of what's happening because the street is clear. And sometimes the descriptions might be a little different for the same scene, so it's important to have them in there explicitly, or the explanation often well matched. So the very high level here is that what we're trying to do is generate a text explanation that somehow really encodes what was important for the vehicle's behavior. And as we said earlier, that's kind of tricky because human beings arguably aren't doing that when they explain. So we've got to try to do at least as well as human explanations, hopefully maybe a little better. And we do that by using attention twice. So there's visual attention that we saw earlier, these attention maps that were being used by the controller in a kind of natural way in line. And then we also use an explanation generator that has its own heat maps. So in other words, when the explanation generator is another neural network, when it's describing a scene, it's attending to certain areas of the scene, and hopefully if it says stop sign, it's actually attending to the stop sign. And by then aligning those two different models, the attention from those two different models, we hope that the explanations are actually salient to what really was driving the vehicle, if you like. Okay. So at Berkeley, we acquired a quite large data set which consisted of these pairs of action descriptions and then justifications. So here's some examples. Basically, people give these in natural language, but they are sort of encouraged or coached into using some kind of delimiter, like these ones, between the description and the explanation. So perhaps most complicated slide I have here. Here's the driving controller again. It has its own attention here, attention map. It's outputting control signals here. And then we generate explanations in one of two ways. The first way is to use the attention from the controller directly as the attention of an attention-driven description module. So we're really forcing it to basically not be able to see anything except what the controller saw. And yeah, that will generally generate some reasonable explanations. A method that works slightly better in practice is to give the explanation module its own visual attention maps. And while you're training, use an alignment loss between these two sets of attention maps, which are frame by frame because it's video. And you're basically teaching this explanation module in general to attend to the same things that the controller is attending to, but you're not forcing it to actually look at the same things necessarily when it's running live. Okay, so that's the loss between those two elements. And I might just in order to stay on time, go a little bit quickly through this. But anyway, it generates explanations. They're not always the same as what a human would say, but they're generally capturing some of the same sense. And so here's the two things running. There's a controller running and generating headings and accelerations. And down here, there's some explanations being generated about what's actually happening. And these are the ones coming from the controller. And, there's a lot of those kind of events of just driving forward without much happening and then stopping. Hopefully it gets that. All right, so let's go. Pretty dense slide. Generally, it does best with the weakly aligned attention, which is having a separate attention map for the explanation generator. And these measures up here are all textual measures to compare the explanations generated by the vehicle with human explanations, which, the human explanations, we want to take some care not to worry too much if we're not doing exactly what the humans are doing, because the humans are not necessarily always explaining. They're sometimes giving normative explanations of what they should have done. Okay, so an interesting thing happened, or is possible once you do this, which is you can start looking at the statistical distribution of words that are coming out of the explanations and compare those with the human explanations. And one word that's underrepresented is pedestrian, which is very disturbing, but perhaps not too surprising because the model is looking at actual video of drivers. Pedestrians have a limited direct effect on the controller. They have a limited causal effect typically because mostly they're walking across intersections where there are red lights or stop signs. So the system already attends to those cues and understands them, and it relatively rarely sees, in the training video, sees pedestrians walking out in the middle of the street and doesn't understand the important semantics of that. So that's obviously a concerning weakness of that kind of model. And so it steered us towards doing what we call advisable models, which is where humans can have direct input on what the vehicle should have done. So, all right, so we've had explainable systems where, we have a description of an action and then a cause. And you can think of that as if you put it backwards, it becomes a kind of a condition-action rule. So I stopped because there was a red light. Generally speaking, you should, which means you can take these descriptions and turn them into rules. And so that's kind of nice because we already have this big data set of condition-action rules coming from BDDX. So what we're hoping, though, is that we can extend them with more general advice, potentially even, a driving manual or other kinds of human texts, or input directly from a driving instructor who sees the vehicle do something that they don't like. So, and yeah, as I said before, an explanation often in practice is an encoding of a normative rule. That is, I stopped because there was a red light, and I should stop if I see a red light. So we took the actual descriptions from all of the BDDX data and turned them back into these kinds of rules, and then put them into the controller. And I think this is, yeah, it's just repeating what I just said. And built this system. I guess I lied to you. This is more complex than the other picture, but basically the key thing here, the thing to pay attention is a sequence-to-sequence model. So basically the front end here is similar to what we saw before. It generates, though, this time instead of descriptions and explanations, it generates just the, the explanation part, which is the condition. So it generates just the conditions, and then we train up a sequence model or a text-to-text translation model, if you think about it that way, which goes from the conditions to the actions. I've got to be careful with that mic. Goes from the conditions to the actions and generates the action that the controller should take based on the text input. So this works a few years old, and things have moved incredibly fast now, and people are doing similar things now with massive language models to sort of produce some kind of description of what's happening and then prompt a general purpose model to produce a reasonable action. But anyway, we didn't have that stuff back a few years ago, so we used the condition action rules sort of reversed to do this. And it helps. With that advice, it actually reshapes the attention map slightly, and you get a little bit more attention on some pedestrians in the right-hand image. And more generally, yeah, this is, yeah, I'll keep going because I want to finish on time. I'll just show you some videos that show the encoded advice from a BDX dataset helping the model in some slightly more difficult conditions. This is stopping at a stop sign, excuse me, a stop light in the rain from a simulator called Carla, which is a widely used locomotive simulator. And yeah, you can see it doesn't quite succeed by itself at stopping under those circumstances. So it stops a little harder on the left. And unfortunately, the video times out when it stops. But and you can see another situation with a a stop sign. How are we going? All right, so keep going. Yeah, so I think I don't want to run over. We did a human evaluation with a short survey that's shown over there, and the quick summary of the results are that with the compiled advice, we were able to do 3 difficult scenarios with higher success rates. We had actually 100% failure rates without the advice built in, and we dropped that to around 25% or less by adding advice. Perhaps the most interesting result from this work is that there's a huge increase in user trust for these kind of systems if you can demonstrate that they're advisable, much more so than just explanations alone. So these are just Likert scale histograms of how popular the respective answers are between I do not trust the system gets a 1 score, through 5, which is I trust the system, a lot. And you can see without any kind of explanation, people generally don't trust the controller very much. It gets 1s and 2s. When you add explanations, you still get mostly 1s and 2s, but you get a few 3, 4s, and 5s, but not very many. And finally, by adding the advice back again, you push it all the way to the right, most of the way to the right, and mostly get positive scores from users. And finally, people thought it was better once you add advice. So it's a useful, it perhaps unexpectedly had more impact than our original goal, which was to improve trust in the system via explanations. We actually found the explanations didn't do very much, but the advisability did. Okay, so I'll stop there.